Right, good morning everybody. This is a talk about dark matter. And I appreciate that maybe some non-astronomers in the audience, so I'll try and explain everything as I go along, but if I use any astronomical terms that you don't understand, hopefully we can pick that up at the end. So this talk is about dark matter. Why is it dark and does it matter? So it's been known for quite a long time now, the best part of a century, that the universe has a dark side. And this little cartoon sums it up. If you can't read it at the bottom there, the professor at the front is saying, after the discovery of antimatter and dark matter, we have just confirmed the existence of doesn't matter, which does not have any influence on the universe whatsoever. I hope to be able to convince you in the next 45 minutes or so that dark matter is important and does have an influence on the universe. So let's think about matter in the universe. What is the universe made of? Well, actually, if we think about all the stuff we do understand when we look out into the universe and try and think about all the stars and galaxies that are out there, if we divide the universe into stuff we know about and stuff we don't know about, it's rather embarrassing to say that the stuff we know about is only 16% of all the matter that actually exists. What is that 16%? You might think, well, it's bound to be stars. Well, actually, no. That 16% is mainly just hydrogen and helium. Gas actually occupies or takes account of most of the matter that we see. Stars only account for about 2% or so of that 16%. And the 1% is just everything else, which I'm not going to talk about. So stars and gas and a little bit of dust is that 16% that we know about. But the elephant in the room is, yeah, but what about that 84% of all the matter that appears to be out there is stuff that we don't really understand. What is this 84%? That's what this talk is about. So what is dark matter? Why is it dark? Well, I'll introduce the idea of matter and light. What is the evidence that there is matter out there that we can't see? Well, there are a number of strands of evidence, and it would take me more than an hour to talk about them all. So I'm just going to pick a couple of those pieces of evidence and describe them to you. So then we can ask, if there's evidence that it exists, well, what actually is it? And there's a couple of candidates for what dark matter might actually be. And then I'll finish with, why does it actually matter? So firstly, why is it dark? Well, the simple answer is it's dark because it's not light. Okay, that's a rather fatuous answer. Let's be a little more clear. Normal matter behaves in a certain way. Ordinary matter or normal matter behaves in a way in which it interacts through what we call the electromagnetic force. Because you and I are made of particles, we're made of protons and neutrons and electrons, we're made of electric material, if you like, particles that have electric charge, and that is why that normal matter interacts with what we call electromagnetic waves, or if you prefer, just light. In other words, ordinary matter can absorb light and emit light. That's what we're used to, if you like. And that's how we detect the existence of matter. We look out into the universe, we see stars that are emitting light, and we might see dark objects that are absorbing light. But essentially, everything we understand when we look out into the universe is based on matter absorbing light or emitting light. But this enigmatic dark matter does none of these things as far as we can tell. And that's why it is still a little bit of a mystery. So we are made of atoms. Hopefully that comes as no surprise to most of you. We are made of atoms. Everything you see around you is made of atoms, and atoms are effectively little beehives with a positively charged nucleus and a load of negatively charged electrons buzzing around that central nucleus like bees in a beehive. And it's the fact that the nucleus is positively charged and the electrons are negatively charged, it's the electric charge that means ordinary matter emits and absorbs light. Dark matter, presumably, must be something else other than a whole load of atoms. So let's have a look at one of the pieces of evidence. We're going to skip over the first and look at the second piece of evidence that dark matter exists. We can think about stars in galaxies. All galaxies rotate, and we can ask how fast are the stars moving in these galaxies. When we look at a galaxy, how can we work out how fast a star is moving? Well, we can use this rather useful result from physics, that if we look at the spectrum, if we take the light of a star and spread it out into its colours and look at the spectrum, as well as the colours, we see certain lines that give us markers, if you like, give us a fingerprint of the spectrum. And when an object is moving away from us, those characteristic lines in the spectrum get shifted towards the red end of the spectrum. We call that a redshift. And if an object is moving towards us, then the characteristic lines in the spectrum get shifted towards the blue. So that means that if we were looking at a little cartoon galaxy on the right hand side here, for instance, if we imagine that there's loads of stars in the spiral arms of a galaxy, if this galaxy is rotating and some of the stars at the position labelled A are moving towards us, then if we look at the spectrum of those stars, we take the starlight and we pass it through a prism or something like that to spread out the colours, we would see the spectrum shifted towards the blue end of the spectrum. Similarly, any stars on the right-hand side that are moving away from us, according to this little cartoon, stars on that side would have their spectra shifted towards the red end of the spectrum. And the speed at which they move dictates how much that shift is. In other words, if we measure the shift, we can work out how fast the stars are moving. So if we do that for lots of different stars in a galaxy, we can work out not only whether the stars are coming towards us or away from us, we can work out how fast they are moving towards or away from us, and hence we can work out how fast this galaxy is spinning. We wouldn't choose a galaxy like that, beautiful though it is, a beautiful spiral galaxy. This one is seen face on. And you can imagine, if this is a sort of Catherine wheel, you can imagine that all stars are moving around in the plane of your screen. And therefore, essentially, none of the stars are moving towards us or away from us. So that would be not a very good candidate for looking at this so-called Doppler shift of the spectrum to work out how fast the stars are moving. It's actually quite difficult to work out how fast stars are moving perpendicular to our line of sight. Using the spectra, it's easy to work out changes towards and away from us. It's quite difficult to work out changes to the left or to the right. So we wouldn't choose a galaxy like that. There's a galaxy edge on, so almost certainly some of the stars are moving towards us and some of the stars are moving away from us. But if we look at a galaxy edge on, then we get this absorbing band of dust that you can see down the middle of this galaxy here. So we are in effect looking at a galaxy almost edge on. Most spiral galaxies are relatively flat, and if we look at them edge on, it's like looking at the edge of a CD. We just get almost a line. And because of the amount of dust in a galaxy, it tends to obscure any variations that we were to see if we were to look right at the edge of the galaxy. So face on is no good, right at the edge is no good. We would pick a galaxy that's at a little more of a jaunty angle to us in order to determine the speeds of stars moving in a galaxy. So that sort of thing there. If the galaxy is rotating, let's not worry about which way it's rotating for the moment. Schematically, this is not real spectra, this is not real data, this is just a cartoon telling us that some of those stars, when we look at their spectra, would be blue shifted, and some of those stars would be red shifted. As it happens, some of the stars would be moving perpendicular to our line of sight, and they wouldn't be either blue or red shifted. Let's not worry about those for the moment. But what would we expect to see, assuming we can look at the spectra of lots of different stars in a galaxy, what would we expect to see with variations in the orbital velocity? In other words, how fast would we expect stars to move as they move around the galaxy? We would expect them to be moving at different speeds depending on how far the stars were from the centre of the galaxy. If we think of a simple case of, for instance, our solar system is a little bit different because all of the mass of our solar system, or essentially 99 point some % of it, is concentrated in the sun. And so if we want to work out how fast planets are going round the Sun is responsible for all of the pulling power, if you like, of the gravity in the solar system. And when we look at how fast planets are moving, we see that here we have Mercury moving at about 50 kilometers per second around the Sun, and you can see the velocity drops. There's the Earth moving at about 30 kilometers around the Sun. The further away from the Sun we go, this scale is in units of so-called astronomical units. 1 astronomical unit is the distance from the Earth to the Sun, so Earth there is at 1 astronomical unit. If we go out to Saturn at about 7 astronomical units, Saturn is only travelling at 10 kilometers a second. It's much further from the Sun. The Sun's gravity has less effect because of that distance, and so Saturn is moving more slowly. And the further out into the solar system we go, the slower and slower and slower the planets are moving, because the effect of the Sun's gravity is getting weaker and weaker and weaker the further away from the centre we go. And roughly speaking, that's what we would expect to see if we were to look at stars further and further and further away from the centre of a galaxy. We would expect a characteristic fall in the speed at which the stars are moving. Now, when we actually look at what's going on here, we have a curve telling us how fast are the stars moving as a function of their distance from the centre, and that graph is superposed on a little picture of the galaxy. For stars that are quite close to the centre of the galaxy, some of the stars are inside the orbit of the star. In other words, they are pulling the star and keeping it in orbit. But of course, there are quite a few stars outside. If we were to pick a star at a distance of 2, in this case, units of thousands of light years, if a star was about 2,000 light years from the centre of the galaxy, then some of the stars would be pulling and keeping that star in orbit, but quite a lot of the stars would be outside the orbit. And that's why the characteristic curve starts to rise here. When we look at the velocity at which a star is moving, as we move from the centre towards the edge of the galaxy, it starts to rise. But what's really important in this context is what happens when we get beyond where we can see most of the light from the galaxy. We can see here a red outline. A galaxy has no edge as such. When we look at the stars in a galaxy, there's no hard and fast line where we can say the galaxy stops here. But we can say, roughly speaking, it looks like 99% of the stars are inside that red outline. So what's going on inside there? The velocity appears to be increasing for those stars. But just as we said for the solar system, once we get outside that red line, most of what's responsible for the gravity appears to be what's inside that red outline. That's where the galaxy appears to be. That's where most of the galaxy appears to be. So when we look at stars beyond, let's say for the sake of argument, 15,000 light years, once stars are beyond that, surely they will be getting more and more and more slow in their motion around the galaxy, because they are much further away from the centre of the galaxy. They are further away from all of the mass which is keeping them in orbit. So this dotted line tells us this is what we would expect if we were to measure the speed of stars further and further and further away from the galaxy. Just like we saw in the solar system, we would expect the speeds to get less and less and less and less the further we go. What do we actually find? Well, for technical reasons, it's a little bit difficult to try and measure stars at that distance, simply because there are so few stars. Remember, we've gone outside the range from which we can see most of the stars. We would have to rely on looking not at stars, but looking at how gas is moving. Now, it doesn't make any difference in the sense that the speed at which a star moves in order to rotate around the galaxy would be the same as the speed at which gas moves. So, apart from that little technical glitch, we can measure how stars move at greater distances. Do they come down the same way that we would expect as for the solar system? No. What we actually find is the speeds sometimes actually get higher. For some galaxies it appears to flatten out, and for some galaxies it actually appears that stars or gas molecules are actually faster and faster and faster, not what we would expect, slower and slower and slower, the further we get from the centre of the galaxy. How can that be? Gravity should be getting weaker the further we get from this galaxy. So surely the objects must be moving more slowly. Anything moving that fast would surely fly away. There's not enough mass in the galaxy to hold on to stars or gas at that huge distance when they're moving that fast. So we come to a conclusion. The galaxy doesn't appear to be enough to hold on to the stars and the gas moving at considerable distance from the centre. It's as if there is some additional mass that is not luminous. Let me just move the camera slightly. It's as if there's some extra mass that is not luminous that is providing extra gravity to keep the stars or to keep the gas molecules orbiting at these high velocities, even a long way outside what we think is the edge of the galaxy. What is that additional mass? Well, we don't know what that additional mass is. We can't see anything there. Let's call it dark matter. That sounds pretty cool. It is something that is providing gravity to make things behave the way we see, to make stars or gas molecules move faster than we would expect. It can't be accounted for simply by looking at all the stars in the galaxy. There must be something else. And it's not just a little bit additional, it's not just an extra 5%, it's not just an extra 10%. The extra mass we need over and above what we can see could be a factor of 2, or a factor of 3, or a factor of 5, or a factor of 10. Huge amounts of mass are going unaccounted for. If we have a little cartoon of what that means in a little animation, galaxies take a long time to rotate, so we can't actually produce a video of a galaxy rotating, but if we could watch it for a few million years, this is what we would see. If a galaxy doesn't have any dark matter in it, then we would expect it to behave like this. The little glitch you see every once in a while is just the video resetting. And at the bottom there you can see a little cartoon of the velocity would be expected to fall away at great distance from the centre. By the time we've got to the edge of the galaxy, we would expect the velocity of the stars to be quite slow. And perhaps you notice that the stars are moving quite quickly close to the centre of the galaxy and quite slowly around the edge. But that's not what we actually see. When we look at lots of different galaxies out there, they all seem to have a particular pattern, and that is that the stars around the outside seem to be moving just as fast as the ones close to the centre. And in the little cartoon graph there, you can see the velocity appears to be roughly the same. No matter how far we go away from the galaxy, the stars seem to be moving at the same speed. Or at least they are not falling as they would if there was no dark matter in existence. So the bottom line is the stars, the outer stars in a galaxy, should be moving quite slowly, but what we actually see is the outer stars in lots of galaxies move a lot faster than we can explain just from the amount of ordinary matter, all of the stars, all of the gas, all of the dust, that we can account for in the galaxy itself. There is a great deal of other stuff there which appears to be pulling on all those stars. Let's look at a different strand of evidence which gives us independent belief that there is something going on out there. Gravitational lensing, as it's called, is quite unlike what we've just looked at, looking at the spectra of stars to see how they're moving. We can calculate mass from the effect it has, the gravitational effect, not on galaxies in a cluster of galaxies or stars in a galaxy, which we've just looked at, but we can work out how much mass exists from its effect on light. Yes, I've already explained that dark matter doesn't interact with light, it doesn't absorb light, it doesn't emit light. That is true, but if dark matter exists, then it has mass. And if it has mass, it has a gravitational effect. And if it has a gravitational effect, not only can it pull on other objects, it can make light bend. And what I mean by that is, let's have a think about a particular example. Let's imagine we're sitting here on Earth in the bottom left, and we're trying to look at a galaxy in the top right, a very distant galaxy, and in between Earth and the distant galaxy there is this cluster, there's this large galaxy cluster here in the middle, and that's a huge mass which is making the light bend. If you wish, you can think about the large mass making space change, and then that space changes producing the change in the direction of the light. It doesn't really matter if you think about it that way. All that matters is that mass can make light bend. For instance, when light passes the sun, it bends. When light passes the earth, it bends, because the sun and the earth are massive objects that can make light bend as it passes around them. We don't normally notice this because it takes a truly massive object to have even a small effect. But if we have a huge galaxy cluster, then it can bend the light from a distant galaxy, and instead of that distant galaxy appearing as a small object, it can make the so-called lensed galaxy appear bigger. It can magnify it just like any lens could, but it can also distort that more distant galaxy. And how much magnification, how much distortion we would expect to see depends on how much mass there is in that lens there that is distorting space and making the light bend. Here's an example of a galaxy which is by pure coincidence in line of sight with a more distant galaxy. So there is a very remote blue galaxy and there is a more red galaxy sitting, as happenstance would have, roughly in our same line of sight. And that rather massive galaxy is making the distant blue galaxy so distorted it appears like a horseshoe, even though that galaxy might be a perfectly normal galaxy in the distance. How can you bend light in such a way to take something close to a point source and distort it into this ridiculous horseshoe shape? How can that possibly happen? Well, the simplest analogy is to think about, for instance, a candle flame here, which is essentially one light source. What happens if you bring a rather imperfect lens up in between that distant source and you? For instance, what about an imperfect lens of the bottom of a wine glass? You can see that in this case, in the top right panel, the single source of light has been distorted and stretched out into these arcs, and in this case seems to produce three bright candles stretched out. And in this particular case, in the bottom right, the candle has been stretched out into two arcs. And if you hold it just in the right position, you might arrange it so that the candle ends up being imaged as one bright ring. And in a slightly different position, you might get an incomplete ring and you end up with a horseshoe. So next time you're having a romantic candlelight supper with your loved one, don't forget to check out the analogue of gravitational lensing by holding up your wine glass, such that the candlelight travels through the base of the wine glass. So here we can see another example of foreground galaxies. These are the ones that are slightly yellowish. They are so massive they're distorting the light that's coming from more distant objects, such as the occasional blue galaxy that you can see here. But most of these blue galaxies you can see are very distorted. These lines that you can see are not errors in the image. These are images of the distant galaxies that have been distorted into lines or rings or arcs by the mass of the galaxy cluster bending the light. How does that help us? Well, by looking at how much a particular galaxy cluster distorts the distant object, we can work out how much mass must there be there. How much mass do we need in order to distort the light in the way we see in these images? Not just in that one image, but in thousands of images taken by Earth-based telescopes and the Hubble Space Telescope. We have lots of examples of how mass of clusters of galaxies have distorted the light from more distant galaxies. And it's a difficult calculation to do, but it is possible to work out from the distorted images how much mass is there in that particular so-called lens. And we find that this is more than we can see. When we look at all the galaxies in the cluster and we work out how many stars there must be, we work out the mass of the entire cluster, it is more in the distortion. When we work out how much do we need to produce that distortion, it's far more than we can account for simply by looking at how many stars there are in all of the galaxies in that cluster that's producing the distortion. Again, it's as if there is some additional mass that we can't see, mass that isn't accounted for simply by looking at all the stars. And that's producing the extra gravity that's needed to bend the light in the particular way that we see in those images. So again, a second piece of evidence for dark matter. There are two additional strands of evidence which I haven't got time to go into at the moment, but they are available in the handout that I'll make available to you if you wanted to look at all four pieces of evidence rather than just these two that I've presented. Okay, I hope you're convinced that there is something out there. There is something that's producing gravity that we can't account for simply by adding up stars and adding up galaxies. But what is it that's actually producing this extra gravity? There are two main candidates for what dark matter, hereafter I'm just abbreviating that to DM. There are two candidates for what dark matter might be. Machos, massive astrophysical compact halo objects, I'll explain that in just a second, and WIMPs, weakly interacting massive particles. You can see that for once physicists have a little bit of a sense of humour by describing the two possible candidates as WIMPs and machos. That's partly reverse engineering on the part of those acronyms. Certainly one of them might be a particle, the other one might be astrophysical objects. Let's just think about those two candidates. Let's take machos first. What's the name? Massive astrophysical compact halo objects. Massive? Well, they have to be massive. We're trying to account for a huge amount of extra gravity, so these objects would have to be massive. Astrophysical simply means we're dealing with large objects, not individual subatomic particles. What do we mean by compact? Well, they would have to be relatively small or we would have seen them already. And what is a halo object? Well, a halo object means when we're looking at a galaxy, we normally see a whole load of stars and probably a bit of dust as well. The halo is the spherical region surrounding the galaxy, which contains not only the galaxy that we see, the stars, the dust, the gas, but also a few globular clusters as well, and other gas that is more difficult to see, extending beyond the visible regions of the galaxy. We don't think there's much there, but maybe that halo is actually full of massive objects that we haven't accounted for yet. Is it possible that the halo around probably every galaxy has a whole load of objects there that are made of ordinary matter? We're not talking about anything exotic. It's the same stuff, effectively the same stuff as you or I, but this stuff doesn't emit any light. Is it possible that the halo of a galaxy contains a huge number of, what could they be? Black holes, or neutron stars, or white dwarfs? Yes, I guess you've already picked up on the fact that surely if they're white dwarfs we would see them. Well, not necessarily. White dwarfs are the leftovers of a star. Once the outer part of a star has been blown away, the very hot core that's left is called a white dwarf. And yes, to start with, a white dwarf is white because it's white hot. But if you wait long enough, a white hot star will cool down. A white dwarf star is not producing any nuclear reactions, it's not producing any energy, it's simply a very hot object that's sitting there cooling off. So if you wait long enough, a white dwarf will eventually be effectively too faint to see. So maybe lots of these were made billions of years ago and they've now all cooled off, and so we've got lots of dark objects sitting in the halo of the galaxy, and it's those objects that are responsible for dark matter. Well, if it is those, this is how science works. You make a conjecture, you make a hypothesis, and then you say, well, if that was the case, can we make a prediction from that? If the halo is full of these black holes, we can't see them because they're black, but is there a way of detecting them? Well, yes, there would be a way of detecting them if they existed. And it's back to what we said a moment ago about lensing, but on a rather different scale. This is called microlensing because we're not talking about having a huge cluster of galaxies bend light. We're talking about a small compact object such as a black hole bending light. On the left-hand side, we can ask what happens if the Earth is staring at one particular star. We've got one of our telescopes trained on a star. What happens if a black hole just happens to pass in the line of sight between us and this distant star? Well, if it were to happen that a black hole just happens to drift into our field of view, as it passes in front of the star, that black hole can bend light just like we saw with gravitational lensing from a cluster, and that can actually make the distant star appear temporarily to be just a little bit brighter. And then the black hole moves on if it's just drifting or moving through space, and then the star retains its original brightness. So if we were to stare at a star and we were to see it suddenly bright and then go faint again, then that might be a candidate for a black hole or some other compact object just happening to pass in front and produce a little bit of lensing. But the chances of that happening, of course, are very low. Staring at one star and waiting for it to happen is not going to be very productive. If we were to expect to see that, we would have to monitor the brightness of thousands or millions of stars in order to hope to see this happen. And that's been an experiment that was being carried out. This is an idea of what our galaxy looks like. It's actually our galaxy seen from the inside, but let's just imagine that we're looking at a galaxy again as seen from just outside, so that we're looking at the galaxy edge on. We are sitting inside the galaxy, but the Milky Way galaxy has a couple of satellites, the so-called Magellanic Clouds down here. So if we imagine that we are sitting inside the galaxy, if we were to stare at stars inside one of the Magellanic Clouds, which has got plenty of stars to look at, millions of stars, if we were to stare at all of the stars in the Magellanic Cloud, then in between us and the Magellanic Cloud, there's this space which is part of the halo of the galaxy. If there are lots of black holes floating around, then some of them sooner or later are going to drift in front of our line of sight to some of these stars in the Magellanic Cloud. So let's do that. Let's spend a few years staring at the stars and seeing if any of them brighten to the extent that we would expect if there are black holes floating around out there. So that experiment has been done. And what is the result? Yes, there are some machos out there. Yes, there are black holes floating around, but not enough to account for the dark matter that we see when we look, for instance, at galaxies rotating or look at the lensing produced by clusters. So machos do exist. There are black holes out there, there are some dead white dwarfs out there, but not enough to account for dark matter. So perhaps dark matter is the alternative, the weakly interacting massive particles. What are they? Well, we don't know. This is, again, a conjecture. This is a hypothesis. Perhaps dark matter is made up of lots of particles we haven't found yet. We know what we are made of. We're made of protons and neutrons and electrons, and we know of a few other particles out there in the particle zoo. And it might be that some of the particle accelerators that are currently switched on, like the Large Hadron Collider in CERN, for instance, might ultimately detect what these particles are. But at the moment, these are hypothesized as possibly particles that exist that could account for dark matter. They must interact through gravity, so they're massive, so they have mass, so they will be pulling on each other and the rest of matter, but they aren't charged like the protons or the electrons that we are made of. So they don't interact through the electromagnetic force, they don't emit light, they don't absorb light. They are similar to another type of particle that you might have heard of called the neutrino. Neutrinos are very lightweight particles that travel very fast. Perhaps these weakly interacting massive particles, these WIMPs, are similar, but they would have to be much heavier and moving more slowly. If they were born in the Big Bang, which of course is a different talk, then it might be that dark matter particles were made with their antimatter equivalents. We are again hypothesizing, and it's possible that WIMPs could end up being caught by the sun. simply because the sun is the biggest source of gravity in our solar system, so perhaps WIMPs would be quite attracted to our sun. So that's where we should be looking. But how do we go about looking for a WIMP that's in the sun? Well, if there are WIMPs in the sun, they might annihilate with each other, the particles and the antiparticles, and make neutrinos, which it is possible to observe on Earth. How would we observe neutrinos on Earth? Well, one option, which we've already tried, is to build a very big water tank. We're interested in neutrino particles anyway because we're interested in how the sun works. So as a sort of a side experiment, it would be possible to look for dark matter particles that also produce neutrinos. How does a large tank of water actually help you find one of these fast-moving particles? Well, again, if we draw an analogy, you may not have seen a jet do this, but you've probably heard one. If a jet moves through the air faster than sound, faster than the air can move effectively, then if a aircraft can move through the air faster than sound, you get a sonic boom. You get a shock wave, and here the shock wave is visible because of the condensation of water. But the important point is, as far as sound is concerned, if you can move faster than sound, you can produce a shock wave. And Cherenkov radiation is the name given to the analogue of that, not with sound, but with light. If it's possible to get a particle to move through a medium, such as air or water, faster than light can travel through the air or through the water, then you get the equivalent of a shock wave, which is visible as a flash of light. So light travels through water more slowly than light travels through a vacuum, and so it is possible for a fast-moving particle to travel through water faster than light can travel through water. And if a fast-moving neutrino travels through this tank, it produces a flash of blue light, the equivalent of a sonic boom, if you like. And that flash of blue light, in principle, can be picked up if you have lots of light sensors surrounding your tank. So all of this is done in the dark, and you have lots of light sensors looking for this characteristic blue flash. And the blue flash is usually set off in the direction that the particle is moving. So if you have lots of detectors, and these detectors down here tell you they've seen a blue flash, and all the detectors over there tell you they haven't, then you've got an idea of which direction the particle was travelling as it came through the tank. And if you measure enough of these, you get an idea of where have these particles come from. Have they come from the sun, or have they come from somewhere else? These light detectors are about the size of a football. Sorry to bring it back to football again, but that's roughly the size of these particular detectors, and they line the entire inside walls and the base and the top. And if you're having difficulty getting scale, that there in the centre is two men inside a dinghy. The water has been taken down so that they can do some maintenance on these light sensors, then it would be refilled with water, and then the experiment switched on. That is still ongoing. So far, no evidence of dark matter, but the experiments are still ongoing. There's another possibility. As well as being perhaps concentrated in the sun, because the sun is a source of gravity in the solar system, thinking on a somewhat larger scale, at the centre of our galaxy there is a huge supermassive black hole with a mass of millions of times the mass of our sun. So maybe WIMPs concentrate there as well. If there are a lot of them in the centre of the Milky Way, then it is thought that there could be annihilation of the dark matter and their antiparticles, producing a lot of gamma rays. And so again, there are experiments that are designed not to look for the dark matter itself, but to look for the signatures of dark matter. We've just seen how that can be done with neutrinos. It can possibly also be done for gamma rays. Again, this is just a reminder that with our galaxy, the centre of our galaxy, which is this big bulge in the middle here, that is just about visible low in the south from England, but if you want to get a good view of the Milky Way centre, then you really want to go to the southern hemisphere. So the idea is to build a load of telescopes. In this particular cartoon, this is shown where in Monument Valley in America, No, it's not going to be there. There's going to be a large number of these telescopes in the southern hemisphere in the Atacama Desert. There's going to be a few in the northern hemisphere as well to balance that out. But if we want to see what's going on from the centre of our galaxy, we want to be in the southern hemisphere, and these telescopes will not be looking at the sun or looking at the Milky Way. They will be simply looking for the blue flashes that would appear if these high energy gamma rays or high energy particles enter the Earth's atmosphere. If they're moving faster than light can travel through the atmosphere, so they'd have to be moving 99.999% the speed of light, then those particles will produce this characteristic blue flash of Cherenkov radiation, the optical analogue of a sonic boom, and this flash can be picked up. This has the advantage that your detector, if you like, is the entire Earth's atmosphere. You're not pointing these telescopes hoping to catch the gamma rays from a distant object. You're allowing these gamma rays or fast-moving particles to be generated in the Earth's atmosphere, and you're looking at huge volumes of the Earth's atmosphere trying to pick up the characteristic blue flash. This telescope will be coming online shortly, not quite ready yet. There are other attempts to detect dark matter, more small-scale attempts. There are various ways of doing it. I'm not going to go through the details of benchtop experiments that might be looking for dark matter. What happens if a dark matter particle comes streaming in? It will probably not interact very strongly with anything we build, but every once in a while a dark matter particle might hit an atom in a detector that we've built and give us a characteristic sign. And there are lots of these experiments going on. You can see the acronyms down the left-hand side there if you fancy going and Googling them to find out more about how these experiments work. There are a number of experiments that are online. Some of these experiments have seen interesting signals, but you have to rule out all ordinary results and other interfering signals that you might get before you can say it looks like we've seen dark matter. So there's been some tantalizing signals, but many of these signals have either been contradictory or at least not yet confirmed as being the existence of dark matter. There is actually another possibility. Maybe there's no such thing as dark matter. Maybe we have simply misunderstood how gravity works. Maybe we only seem to need dark matter because we've got some of our equations wrong. Maybe gravity works differently at different scales. Newton said the gravity that's pulling an apple to the Earth is the same as the gravity that's keeping the moon in orbit around the Earth, and ultimately it's the same as the gravity keeping the sun going around the Milky Way or the Milky Way moving through a galaxy cluster. But maybe it's different. On the scale of the universe, cosmological gravity, maybe that works differently than gravity on the scale of a galaxy, or gravity on the scale of the solar system, or gravity on the scale of the Earth and an apple. Maybe it is different and we have to modify gravity, modify our equations of gravity to take into account what appears to be dark matter. And you can indeed get rid of dark matter if you tweak the theory. But if you tweak the theory, it generates all sorts of other problems of its own. And so although this idea of modifying gravity, so-called modified Newtonian dynamics, or MOND, some people still claim that this is the way to go, but it tends to produce more problems than it solves. So does it really matter? Who cares how fast a galaxy actually rotates? What are the consequences if dark matter exists or dark matter doesn't exist? Well, we can do simulations to work out how galaxies came to be. After the Big Bang, how did we end up with galaxies and stars the way we see them today? If we don't put dark matter into those simulations, we can't get things to work. We can't end up with a universe which agrees with the one that we seem to be living in, unless that universe has got a substantial amount of dark matter in it. So a long, long time ago, 13.8 billion years ago, everything that we currently see in the observable universe used to be inside a volume about the size of a golf ball. And the golf ball had dimples in it. These dimples were small variations in density of the early universe. And over time, those small variations in density gave rise to what we see today. If we take a little cube of the universe and fill it with matter, but fill it with matter where the variations, the density of matter has got small variations from point to point, if we let gravity do its stuff, then we find the universe collapses and we end up with filaments and knots where galaxies will one day exist, and some regions then become underdense and we end up with voids, and we end up with this web structure, this cosmic web, whereby the densest parts are where galaxies will exist and ultimately we will exist, and other regions which appear to be underdense. But the point is that the universe came into existence 13.8 billion years ago, and we've ended up with something that looks like this now. When we look out into the universe, this is what we see: galaxies and filaments and voids. But we can't simulate that. We can't get the simulations to work in 13.8 billion years unless dark matter is in the mix. If we don't have dark matter, the universe doesn't collapse fast enough, and we can't get to where we are now in a mere 13.8 billion years. So it appears to be absolutely necessary for dark matter to exist in order for galaxies to exist, in order for stars to exist, and hence planets, and hence us. So as far as we can tell, we would not exist if it were not for dark matter. On a huge scale, this is what the universe looks like: a web, or a foam, if you like. If we zoom in, we see the detail of galaxies, and if we were to zoom in further, stars. But we absolutely need dark matter for it to exist. So I've been telling you about what dark matter is. Why is it dark? Because of the nature of how matter interacts with light. I've given you 2 of the 4 pieces of evidence. The handout will give you the other 2 as well, if you're interested. What are the candidates for dark matter? It appears to be either objects like black holes, so-called machos, or it appears to be a new particle we haven't found yet, a WIMP. So far, it doesn't look like machos, but we haven't found the WIMPs. And does it matter? Well, without dark matter, it would appear we would not exist. So yes, it matters. Thank you all for listening.